Hey, so let me talk a little bit about cross entropy. Um, with the way that you should think about cross entropy is that it's basically just the average probability of some sequence of events as assessed by some um, probabilistic model. So I've got on this cross entropy example spreadsheet three different like probabilistic. They're kind of just stupid probabilistic ways of assessing a series of node onsets. And this first one, let's call it the complex model. So the complex model says that on the downbeat, you might get, there's like a 10% chance that you'll get more than 3 node onsets. On the downbeat, you're like 40% likely to have 3 node onsets. Two, 30%, one, 10%, zero, 10%, and so on. And so like what this complex model is giving you is just like how much should you expect to have each of these numbers of node onsets on a downbeat on each beat in the measure. And you can imagine like learning something like this from a data set. Like you could just like go through a data set and say, hey, on average, how many node onsets do you tend to see on the downbeat? And like maybe 40% of the time you have 3 node onsets on a downbeat. 30% of the time it's 2. So you could imagine learning this from a corpus. I just made this up, but in the reading that you're going to do, it's all very connected to a corpus or to a data set. So then what you can do is then take a series of node onsets and assess how probable they are. So you've got a downbeat with 4 node onsets. This is the Aloha Oi that we worked on in class today. So there's 4, 0, 1, 0, 3, 1, and so on. And like the downbeat has 4, and so we'd say, well, how likely is that in this model? Oh, it's 0.1. All right, so there's a 10% chance of that happening. How then we've got this intervening 8th note. So let's see if we say the 8th note, how likely was there to be nothing happening on the alternate 8th note? 55%. Great. This is very probable. On the quarter note, there's 1. So let's look at the quarter note. There was 1. Oh, 45%. Great. And so on and so on. And so we can fill in this along those lines. And through the magic of television, I will come back and this will all be filled in. All right, so now this is all filled in. So taking the average is basically what cross entropy does, but it approaches it in a way that like is unique to probabilities, because in order to get the probability of a whole sequence, if you like, so hey, how likely are 2 heads to be to flip a coin and have 2 heads in a row? Well, it's 0.5, not, you don't average 0.5 and 0.5, it's 0.5 times 0.5. So it's like 0.25 is 1/4 is the likelihood that if you flip a coin, you'll get 2 heads in a row, right? And so like to take the probability of the whole sequence, you're going to have to take this times this times this times this and so on. So you're taking the product of the sequence, and that ends up giving you a very small number. So to combat that small number, we use the logarithm in our probability calculations. So what you do is in a way, this is sort of arbitrary because you're just trying to make sure you don't get this low number. But another benefit of logarithms is that it allows you to take the average just like by adding together and then dividing by the number that you've got, as opposed to having to multiply them together. Most folks take the logarithm base 2 for this, and then you can just take the average of that, and it gives you the sort of the average log probability of the sequence, and that is you have to take the negative because logs give you negatives. So that gives you the average log probability of the sequence. Now I'm going. Now there's other models here, and what we can do is we can say, hey, what predicts this the best? And that is done by seeing what gives you the best cross entropy. So I've made two other models that can assess the sequence. So here we've got like it just says strong and weaks. So if you just say, okay, if this is strong and this is weak and this is strong and this is weak, how probabilities? So the first one is it's 3 plus and it was strong. So let's say that it's 0.2. It's 0 and it's weak, 0.2 there as well, and so on. So I'm going to finish the sequence, and through the magic of television, I'll be right back. And now I've completed this, and I can do exactly the same thing, and I can take the log of that. And so here's the log probabilities of all of these, and then I can average those, and you get the average log probability of that. I made one more model, which is just that like everything is equally likely. So it's the so we'll call this the binary model over here, because it's just tells you what happens on strong and weak piece, and this is the even model. So here everything is going to be 0.2. Everything in this model is 20% likely, and then we can do exactly the same thing, average, and it's that. Now one thing about cross entropy is that the better it predicts, the lower the number. It's a little bit unintuitive, but what entropy is it the word entropy is it's the disorder of a system. So like what cross entropy does is it says how well does the model how much disorder does the model give the system. And so like a higher number means that there's more disorder and the model hasn't done a good job of organizing it well. Whereas closer to 0 means that you've got the model is ordering it very well. It's predicting it very well. And so here, this model, the sort of the more complicated model, is in fact predicting it better than these other two. This is another outcropping of using logs, is that it sort of flips the notion of like average, of what the average number means, is that the higher it is, the lower the probability, the worse it's being explained. So the higher number means lower probability, the lower number means higher probability, the better it's being explained. But what's interesting is that this dumb binary model, even though it has more gradations than the everything's even model, it predicts it worse. So it has a higher disorderly number, a higher cross entropy than the even model. But what's best is the more nuanced model. It orders the information better. So that's because it has the lower number. Lower orders it better. Higher, more disorder. So that's what cross entropy is. Think about it as like averaging probabilities, but it's then converting it into this representation of order and disorder. That the higher the number, the more disorder there is. The lower the number, the less disorder. The more organization, the better a sequence is being predicted.